So database locking fixes our race conditions problem, but you see it creates a massive bottleneck. So we looked at optimistic locking, pessimistic locking, atomic updates. So whether threads are maybe waiting for row locks or just fighting for resources, 1,000 users will instantly crash our connections that we have made to the HikariCP pool. So to survive this thundering herd, we need to decouple the database from the incoming traffic. And this is where AWS SQS comes into the picture. So AWS SQS is it stands for Simple Queue Service. It's a fully managed asynchronous message queuing service from AWS, and there are three main cogs related to SQS. You have a producer, you have a queue, and you have a consumer. So these are the main cogs. Producer will forward a message to a queue. Consumer then polls for messages from this queue, and consumer takes this message, processes it, and deletes the message. So like I mentioned, SQS is the solution here because you see it acts as the shock absorber. It, because we are decoupling it like I mentioned earlier, it separates the database from the actual incoming traffic. So basically those maybe thousands of requests that come in, all of those requests get put into a single filed line, and that is, in a very nutshell overview, that is what AWS SQS is. So I have created a queue here. We can have a look. Yeah, so we have ticket sales queue over here, and if I were to edit this, yeah, so there are lots of options here, but let's just take a look at what this visibility timeout is. So visibility timeout is basically the moment a message is taken by a consumer, a kind of timer will run, and when this timer runs, that message becomes visible only to a particular consumer. It will become invisible to the other consumers during that certain time limit. And assuming that this time runs out and the consumer, say, hasn't finished processing this message, SQS will make this message visible to other consumers. So in a nutshell, this is kind of what AWS SQS is. So let's maybe have a look at the actual process, like I mentioned, where you have a producer, a queue, and a consumer. Maybe let's see if we can put it into some sort of diagram to better visualize this process. So let's have a look at a diagrammatic representation of the process of SQS. So the first thing that we have in SQS is you have a producer which sends your particular payload to a queue. So of course by payload I mean message here. Basically the producer has the job of converting the payload that you send into a JSON, because AWS SQS can't really understand the data type of the payload that you're sending. So you will have to serialize it. You will have to convert it into JSON, and you will have to send it to the queue, and that's pretty much what the job of the producer is. So producer takes this payload and it sends it to the queue, and the queue basically stores the messages that it receives from the producer. So we have the other cog, which is the consumer. So what the consumer does is the consumer polls for messages from this queue. It keeps asking the queue, are there any new messages, are there any new messages, and what it does is it takes on messages, and this consumer takes this message and it processes the message, it does whatever logic that it needs to do. And of course, remember, consumer gets the message in a format. It gets the message in a serialized format. So it needs to deserialize it so that it can actually work with the logic. And once it has finished deserializing it and running the core business logic, after all of that, consumer has a job just to delete the message. Now AWS SQS, it runs a lot deeper than this. You could specify how many messages a consumer can poll and process at a time, but just for this demonstration I'm keeping it simple. So to put it in a nutshell, this is what the process of SQS is. So coming into the code, so before we actually get into the whole SQS producer consumer logic and how we use the AWS SDK for this, it's kind of, I think it's necessary for me to really explain the configurations that we have to do in order to get SQS and AWS up and running first. So the new Spring Cloud AWS is quite handy because it takes care of a lot of things which the old Spring Cloud AWS had to do, which was quite painful because we had to manually configure a lot of things. So for example, we had to manually write the configuration class for AWS credentials, and then you had to manually write the code to serialize and deserialize using object mapper, and then you had to write manual acknowledgement logic like on success and such. So the new Spring Cloud AWS takes care of all of this under the hood. So maybe let's start with the application of properties and the pom.xml to kind of understand what's really going on here. So when it comes to the credentials, all that you have to do is simply give your access key and your secret access key, which you can get from your IAM user roles. And after that, you have to define the region in which your SQS queue is. So in this case, it's in Mumbai, which is AP-South-1. And after that, you need to pass in a custom key, which is the name of your SQS queue. So regarding configurations, that's what we have to do. So when it comes to the pom.xml, our dependency management, so the first thing that we have to do is we have to define a BOM, which means a bill of management. See what this bill of management does is, I'll highlight it right over here. See what this bill of management does is, it basically makes sure that all of the versions of your dependencies don't clash with each other. It makes sure that all of the versions of these dependencies can safely run while working with other dependencies. That's pretty much what a BOM does, bill of management. So we also need to pass in other dependencies like Spring Cloud AWS Starter, which handles configurations for us after we defined it in the application or properties. It takes care of that under the hood. There's a lot of abstraction here, but just to keep it simple, that's how we do it. And we also are using AWS SQS here, so we also need to use the dependency of AWS SQS, which is Spring Cloud AWS Starter SQS. So this dependency will kind of give us the required methods to work with for producer, consumer logic and such. So regarding setting up, that's pretty much all that there is to it. So next, let's have a look at the actual controller logic, the producer logic, the consumer logic, and let's see how it integrates into our project. So let's have a look at the actual implementation of producer and consumer. So first of all, we need to kind of remember that key, the custom key that we defined in application.properties, the ticket sales queue key. So we need to pass it into our construct of the controller using the annotation value. So the controller here is pretty much the logic for the producer. I mean, if you take a look at my method for post mapping, what that does is it does act as the producer. The producer's logic is handled by the controller. So like I mentioned earlier, the producer has to take in the payload and serialize it and send it to the queue. So SQS template.send, we define the queue name and we attach the payload to it as well. So this method will pretty much send those two components to the queue. It serializes it and sends it to the queue. I have made another injection here called store state. And what really is this store state? So store state has something to do with atomic variables, and I will come to that. So that is pretty much what the producer does here. It takes in the payload, so in this case it's a order DTO, it serializes it and it sends it to the queue. So now let's take a look at our consumer logic over here. So in a real system, you wouldn't have both your producer and consumer logic in the same project, because in most cases it's going to be in different projects. But since this is a demo, I have included both the producer and the consumer in one project. So basically the consumer only, we do the database related logic. So basically this consumer receives the message, deserializes it, and it does the relevant business logic. So in this annotation SQS listener, basically what it does is it deserializes and it kind of gets the queue name from the parameters that you pass in. You don't have to use the value annotation like earlier. Just passing in the queue name from your custom key that you define in application.properties is enough. So that is what SQS listener annotation does. And another thing which we need to remember, we have to make sure that the data type of the object that we have passed in the arguments of the method should be the same as that of the producer. What we are sending in producer, the data type of the payload that we are sending in the producer should match what you are defining in your consumer class. So having a look at this logic, again we simulate the weight and then we do the atomic updates, and finally we create the order and we set it as such. So the core logic hasn't changed all that much. We are simply moving it around because of this implementation of SQS. So now let's take a look at what this store state is. So basically SQS is kind of an expensive operation if you think about it. By expensive I mean it does actually cost resources. So you wouldn't necessarily send a payload to SQS unless there actually is a ticket left to sell, right? So which is why you need to kind of make sure that there are tickets left to sell before you send your payload. So, but there is a question. If we do a good old check where let's say you write a method to get the quantity or whatever that is, won't you risk a race condition again? Because won't those threads kind of save their state right after you check, and won't that be repeated? And won't you be introducing a race condition again? So the solution to this is to use atomic variables. Basically, these threads, they read their values from an L1, L2 cache. They don't really they don't necessarily grab the values from the RAM. So all that stale data is in the L1, L2 cache. So what if we could get these threads to read directly from the RAM, which is actual fresh data? And what if we could implement a way where the moment something changes in state, the some process runs and it updates all of these threads saying that, look here, your data is stale, you need to go back to the RAM and fetch whatever it is. And to put it very simply, that's what atomic variables are. So atomic variables comes in different forms. So you have atomic variables, you have atomic integers and such. But here we will be looking at atomic boolean. So if we have a look at the class, if we have a look at the class, we have setters to set the initial value, to set the value as true. We have a getter to check if it has sold out. So that is pretty much what the logic of atomic boolean is. We have getters, we have setters, and of course we have to declare an initial value. So if we maybe go back to our consumer class, see, right after we have done the logic to check if the order status has failed, see, we immediately call this setter method to say that the ticket has sold out, and that boolean flag, the boolean flag is sold out, becomes true now. So the moment it becomes true, it broadcasts a message to all of the threads saying that what they have checked is stale and that they should read, or rather fetch, from the RAM. Because see, here in our controller, in this check is sold out, the getter method, here we are getting all of the threads to check if the tickets are sold out. So to put it into perspective, the moment you mark it as sold out, the RAM gets updated and it broadcasts a message to all of the threads saying that the data that you have is stale, what you have read is stale, so go and fetch the new data from the RAM, which says that the values are now true, which means that the tickets have actually sold out. Alright, so that's pretty much what the logic of SQS is. So let's run this in K6 and let's have a look at what the logs will actually look like. I mean, it should work, right? We have done our database locking here. We have handled the traffic as well. So will it work? So let's fire up the K6 script and let's have a look at what it does. Let's now run the K6 script and let's see whether if SQS really is the best solution for this, and whether if it acts as a really good shock absorber. So if we have a look at my code, so Spring is running. So let me quickly make this quantity as 1. Alright, quantity is now 1. And so let's now run the K6 script. Quantity is now 1, 1000 concurrent users. Let's see if SQS can really handle this thundering herd problem. Alright, so here it says that 653 were queued. So this begs the question, how many tickets did we actually sell? I mean, it says that 653 were bought. Is it? Maybe let's have a look at the users table just to see what really went wrong here. So coming to my database. So if I were to run this SQL query to check, first of all, how many quantity that I have. Yes, so we have successfully sold the last ticket. And if I go into my order table, so it seems like I have successfully sold one ticket. The user, or rather the thread that was the fastest, was able to successfully buy that last ticket. So we have a lot of failed requests, and let's just check how many we have here. 653 orders. Maybe let's have a look at that results again. So what what really happened here? So from those 1,000 requests, if you have a look at all of these mystery codes here, and I believe there were some request fails as well. See, what happened here was some of the 1,000 requests got bounced off from the network because of the TCP UDP backlog, and the other requests, the other 653 requests, were able to get into our app, and all of them hit the endpoint at the same time. And you see, from those 653, only one ticket was sold out, right? So we don't really see any 409 sold out or anything as such, because, well, if SQS is a waiting room, we got all 653 in. None were left out. Hence, there were no threads to which you could show the sold out to. And I believe that we have actually solved this issue. So just for the sake of curiosity, maybe let's have a look at our logs here, which I have implemented. So if I were to go into, so it seems like the consumer has sent most of these threads to the queue as shown by the logs over here. And yeah, so to put it very simply, that's how we solve concurrent threads in a thundering herd where there's only one ticket left to sell. Alright, so that pretty much concludes this video. So we saw about race conditions, what exactly causes these race conditions, the solutions that we can implement to solving this flavor of race conditions, the lost update problem, by implementing various methods like pessimistic locking, optimistic locking, atomic updates. And we also saw how it is that we can handle the massive traffic of users coming in, the thousands of requests hitting that endpoint, and how we can use AWS as a shock absorber.